Okay, so hello, welcome back. So we're going on with session 2 for the N-Body workshop today. And today's main objective is to cover how and what exactly we're doing when we are setting up the N-Body simulation, as in how do we set the initial conditions. And also just to actually compile the code and run through it once, at least for Gadget 2's applications. I realize there are some people that uses Ramses and other types of N-Body code, but the workflow should be almost identical. And also, because the similar structure between the two, we might as well also cover power spectrum estimation.
It should be calculating the power spectrum is their objective.
Yeah, so there are many like physical quantities that you can check to see what your simulation is doing. And I think the power spectrum is probably the most common one. That and Halo catalogs.
Depends on what you're doing.
Yeah. Okay, so for what I've been doing, at least, like power spectrum is like the primary output that we get out. So let's just look through that. Okay, so anyway, if we look at initial conditions, what we essentially want to do, like we said yesterday, was we want to start not at the literal beginning of the universe, but slide in somewhere in the middle as some initial redshift. That's after all the high energy physics have quietened down, but before the structural formation have started becoming nonlinear. So in order to save as much computation time as we can. So the biggest question is, how do we actually put particles into a box so that the box reflects a real universe with the cosmology that we want to study? Or even if it's not a real universe, how do we actually represent the cosmology with some particle distribution? And the answer to this, of course, you should have guessed, is Russian, and is my boy Yakov local babushka Zeldovich. So I don't know how it was. The B stands for something else. Borisovich, yeah, that's it. Okay. But so the whole process is called, okay, at least the first order one is the Zeldovich approximation. So what the Zeldovich approximation essentially is doing is giving you a way of connecting your Eulerian coordinate with your Lagrangian coordinates. Yeah. So here, the X on the left-hand side, these are what we call Eulerian coordinates. So these are like, imagine you have your box, and I set up a grid in there. And at every point on this grid, so you can ask a question, okay, how much particles, how much energy density do I have? What's the velocity of the fluid passing through this particular point? What's the total density at this point? So you can ask this question at every single one of these grid points. And if you're asking it like a stationary observer kind of concept, this is the Eulerian framework where you are the observer is stationary and you're simply looking at that point, what is the state of the system? Whereas on the right-hand side, you have the Lagrangian description or the Lagrangian coordinates. What the Lagrangian coordinates is doing is, rather than sitting in a stationary position in the box and asking what's happening, you instead partition the fluid, your matter fluid. So if this is your CDM fluid, I cut them into tiny little parcels. And for one of these little parcels, I put a little data recorder or something in there. And I follow this parcel around. So as this fluid is flowing or like dispersing and changing shapes, this little parcel probably follows the flow somewhere and it moves around and it changes velocity as it gets moved around. And I keep track of what's happening to this particular parcel, and I follow this particular parcel around for the entire time. And I can do this for all the different little partitions of this entire fluid. So this framework is a Lagrangian framework where you're following a particular section. Whereas the Eulerian framework, you are stationary and you let the fluid run through you and you ask what is happening there. Is that like a roughly? Yeah. So the Zeldovich approximation allows us to connect these two coordinate systems to each other. And the advantage of doing this is because the easiest way for us to set up the simulation is to place particles on a regular homogeneous grid. So if we set up a grid in a box and we simply put one particle on every single grid point like this. And of course, inside a box as well. But it's harder to draw, so like you get the idea. So you have a 3D grid and you put a particle on every single grid. So right now, this box is completely homogeneous. And if you let this run as a simulation, nothing will happen because gravity is going to be balanced out in every single direction. So no overdensity means nothing happens. So what these initial positions are the Q that we had before in the equation, X equals Q plus psi. So this Q is the initial position that we put down the particles. So the initial Lagrangian position. And we want to move these particles slightly in some systematic way so that after we shift them off the grid position, so we push these particles around with some scheme that we're going to derive, well, like under the Zeldovich approximation. So I shift all the particles by some amount. After I shift them, these particles will then form a non-homogeneous distribution. And how much I shift these each little particle is described by this field psi, which is a function of Q and T. So this is the Lagrangian displacement field. So as it suggests, it tells you how do you displace the particles. And after you have displaced the particles, and then you go into the box and you ask what's the statistical properties of all the particles inside the box. So the statistical correlations they have, for example, is a question you can ask. And this correlation should correspond to some real cosmological predictions. So if you have design some cosmology, and then you can ask what's the 2-point correlation function in this cosmology. And after I have displaced the particles from the initial position, the box should reflect the same 2-point correlation. For example, that's one way of demanding how to displace the particles. Of course, you can go higher in order. You can also demand that the particle's 3-point correlation also matches the cosmology of your choice and can go on so on and so forth. But for what we're doing in Gadget 2, we only care about the 2-point correlation function. So we have to just make sure that the 2-point correlation of the final position of the particles is correctly reflected as the some real cosmological predictions.
So I guess what you mean is that if you displace all your particles and then you use your cloud in cell method to smear the particles back onto the grid points, and then you ask what's the density on each grid point, that should reflect the cosmology that you want to investigate initially.
Right. Yeah.
Okay.
Yeah. So So the because you can have the 2-point correlation function is actually for the density perturbations. Yeah. Right. So yeah, so under this, then the X is the final position that the particles will end up on. Q is the initial grid position. And psi is how much to move them. So obviously we want the final position, and the initial position is just put it on a grid. So the problem, the question we want to answer for the Zeldovich approximation is, how do we derive this psi? If we can derive this psi field, then we know how to move the particles onto the correct position for the starting cosmology, starting redshift in that cosmology. So, okay, so to do this, you could do this via proper Lagrangian perturbation theory, but I'm going to cheat a bit here and just do like a sort of like a bastardized mixture of the two to get the point across. So we assume an ansatz that the Lagrangian displacement field, which is a function of the Lagrangian initial position q and the time, can be separated into a time-only component, d, and a space-only component, s. So this d has a physical name. Where's the pen? Here we go. So this is the linear growth factor. So the linear growth factor, you can think of it as during the early universe, after CMB and all that happening, your initial primordial power spectrum, which is the power spectrum you get out of after inflation. After inflation, you get a primordial power spectrum. This primordial spectrum and then gets modified by the CMB transfer function. So the primordial power spectrum is probably really boring. So it's probably just going to be a flat line that's slightly tilted. And the CMB transfer function will then turn this flat line into the normal kind of power spectrum. Okay, probably some more baryonic wiggles here, but it will turn it into this. But then after the matter domination happens, all the clustering would grow. So the late time matter dominated growth acts as a homogeneous shift if you assume CDM only. Acts as a homogeneous shift that takes this power spectrum and just simply shifts it upwards, so then it grows higher at later times. So the linear growth factor that we have here, the D, refers to this growth. So this homogeneous shift upwards is described by D of T. So the longer you give it, the higher this power spectrum will grow. So, okay, and we can derive this linear growth factor quite easily from the fluid equation that we had before. So if you recall, we had the continuity and the Euler equation. So I rewrite them in a slightly more convenient format. So the delta dot plus 1 on A of V is equal to 0. So here delta is defined as the density you have at some point x at some time t minus the average density of the universe, which is a function just t, divided by the average density of the universe. So this is the density contrast. So the continuity equation tells you how the density contrast evolves, and then also the Euler equation for V dot plus HV plus 1 on A. The peculiar potential is equal to 0. And the Poisson equation. So you can combine the first, you can combine all of these equations together into one second order differential equation, which is written as d double dot plus 2h delta dot minus 4 pi g rho bar delta is equal to 0. So here you combine the three equations into one second order differential equation, and you can solve this equation quite easily. And we just want to define d of t to be delta of xt divided by delta naught of xt. So delta naught is simply the density contrast at redshift of 0. Okay, I won't say redshift 0, at today, because you can technically normalize this to any redshift. So this is thought of as like the final redshift that you care about. So you can normalize this to whenever you want. But the common practice is to normalize this to redshift of 0, known as also called today. So today refers to 0, 0, but you could do this for high redshifts. So since this is a linear differential equation, dividing it by a constant factor is not going to change it. So this whole equation could just be rewritten for d. So d double dot plus 2h d dot minus 4 pi g rho bar d is equal to 0. And if you just solve this equation for some Hubble rate and for some average density that you want in your cosmology, then you'll be able to get the linear growth factor out for the cosmology that you're interested in. So this will tell you how much the power spectrum will homogeneously grow at late time. So that's the first part done. So we now have a very clear way of finding D. So the thing that's remaining for finding the whole displacement field is this S. How do we get this S field? And to look at the S, to get the S field, we have to look at the derivative of the separable ansatz. So our Eulerian position X equals Q plus psi vector. We want to take the derivative, so we want to look at the velocity. And the Q is a initial position that you place a particle down, so it has no time dependence. Once you put it down, it stays there. Or like that position is predetermined. So this Q doesn't evolve with time, so it drops out in time derivative. So all you have is the D dot and S, which depends only on position, so it also doesn't have a time derivative. And this whole thing, because V, which was previously defined as the proper velocity, is A x dot. So this whole thing is equal to 1 on A times the proper velocity. So from this, we know that the proper velocity is given as A d dot S. And if you look at this equation, you can put this into the Euler equation, because the Euler equation, where's my Euler equation? Did I delete it? I might have deleted it. Oh no. Okay, so yeah, so in the Euler equation, if you remember, it's in terms of V. So yeah, so V dot plus HV plus 1 on A del phi. That could be written as A D double dot S plus 2 A dot D dot S plus 1 on A del phi equals 0. So I just put this into this step, the Euler equation here, and take the derivative. And this is what we get. And now we can find that minus del phi is A squared D double dot plus 2 A dot D dot S. And here you can see the first, how did I get this? Oh yeah, sorry. So this part, if you compare this to the growth equation we had before, which was D double dot plus 2HD is equal to 4 pi G rho bar on D. So this is essentially this, if you rewrite the H as A dot on A. So we can substitute this right-hand side into there. So minus del phi is equal to 4 pi G A squared rho bar D of T S of Q. Yeah, so now we have an expression for minus del phi. And we also can compare this to the Poisson equation. So del square phi equals 4 pi G A squared rho bar delta. So now if you look at these two equations, if they both have to be true, it's not hard to convince yourself that D of T times S of Q must equal the negative del of some field chi, and this field chi, the Laplacian of it must be delta. So in order to satisfy these two simultaneously, this has to be true. So yeah, so we can redefine chi a bit. So rather than having chi being a time-dependent field, because right now chi depends on both D and S, we redefine chi to be time-independent. So we call S of Q minus del, the old chi divided by d. So this would just be our new chi, which is no longer dependent on time. And so del square chi is equal to delta on d of t. And if you remember, the definition for d is delta on delta naught. So this is by definition just delta naught. Oh, I just redefined it by saying S of Q is equal to minus del chi on D, and then recall this thing. Okay, yeah. Yeah, so just want to get rid of the time dependence in that case. Yeah. Okay, yeah, so what this now tells us, so this is the important result. So what this result tells us is that we can relate delta naught, which is the density contrast today. So delta naught could be related to the square root of the power spectrum today. Okay, yeah, so it could be related, so not by definition, I suppose. So from the power, if we can extract the power spectrum from some linear Boltzmann code like class or CAM, then we can from this get delta naught. And then once we have delta naught, using this, these two formula, we can then find the displacement field S, and in turn find the entire displacement field psi of Q and T. So the Lagrangian displacement field can be completely derived from the density contrast. And that's the main result from the Zeldovich approximation, is that we only need to find delta naught in order to get the initial how to displace our particle at the initial time. So we can solve for the field chi. So we want to find what the chi field actually is. So to do that, we go to Fourier space. So once we go to Fourier space, delta naught of k is equal to, rather than the Laplacian, so it was the Laplacian gets replaced by just minus k squared, chi of k. So then the chi field in k space is given by minus delta naught on k squared. And now, in terms of math, we call the density contrast of the universe to be a Gaussian random field or Gaussian white noise that with zero mean and standard deviation given by the square root of the power, given by the power spectrum, P of K. So once we get this kind of description, think of delta naught as just a Gaussian white noise field with zero mean and the standard deviation, then we can write the right-hand side of this as minus 1 on k squared, the standard deviation times by a randomly drawn amplitude and a randomly drawn phase. So as long as this random part satisfies the white noise requirement, then this whole thing, this whole thing that makes sense. So, okay, so what this means is you can rewrite R of k e to the I phi k as R1 plus I R2, and R1 and R2 are white noise.
How do you make sure you don't have too many degrees of freedom? Because in real space, every point has to have a real value.
Yep.
And now you're in Fourier space and you're doing everything complex. So suddenly you have 3 more degrees of freedom.
Oh yeah, so that's a good point. So if you're doing the Fourier transform of a real field to the Fourier field, then you get the conjugation symmetry, right? So whatever random noise you assign for the value k, you have to give the same one for the minus k.
Yeah, okay.
Yeah, so that will ensure that when you Fourier transform back, you get a purely real field. Yeah, that's a really good point. And yeah, that will be important later on when we look at how NGenic implements this. So yeah, so now we have a definition for chi, which is in terms of a power spectrum that, okay, I should probably put P0, so that's today. So given a power spectrum and some random numbers that we can draw from like any kind of RNG generator from like GSL, for example. So this is easy. So now with chi defined, we can then define S, because S was, remember, the S in K. S in real space was the minus derivative of chi. So in K space, we just pick up a factor of minus IK times chi of K. So then that will give me I times K on K squared, square root of P of K, RK e to the I phi K. And the whole displacement field psi, in K space, is given to you by I K on K squared, square root of P naught of K, times by the D squared of T. So remember, psi is given by D times S, but I'm now putting a D inside the square root, times R of K e to the I phi K. So if you're looking at this, the power spectrum and the growth factor being lumped together, what that essentially means, like I said before, the growth factor just tells you how much your power spectrum gets homogeneously shifted upwards as time goes along. So this is like the inverse action of that. So I'm taking the power spectrum today and I'm pushing it back down by how much time that I want to go back. So going back to the starting redshift, this D squared will tell me how much I have to scale the power spectrum lower. So these two combine to give the power spectrum at the initial time that I'm interested in, given that I find out what the D squared at the initial time was. So the displacement field in K space at the initial time is just I, K, K squared, square root of P of K, T initial, and our random number. So that's it. So you just have to compute this from some linear Boltzmann code. So class can give it to you, Cam can give it to you, CMB fast if you're a little older. So yeah, so now you have a very clear recipe on how to go from linear theory to displacing the particles to accurately represent the cosmology that we are interested in. Cosmics. I've never even heard of that. Okay. Oh god, that's like 90s. 80s. Oh, okay. Before my time. All right, so, okay, so now that we have the displacement field, we're still actually missing one more thing, because at the beginning of the simulation, we can't just move the particles and then leave them there, because then they will be completely stationary and they will only start pulled by gravity afterwards. But in reality, these particles will probably have some velocity already. Even cold dark matter would have some velocity from the previous gravitational interactions before we started the simulation. So we need to find a way to find the corresponding velocity field to give the particles an initial kick for them to have something to start, proper velocity to start with. So this is quite easy, because now we already derived the displacement field. The velocity field is just the derivative. So proper velocity is defined as a x dot, and that's just a d dot s, given the definition of x that we had before. So if you rewrite this as a times a dot on a, d log d, d log a, psi of q, not st. So that's nothing fancy. I just added an extra d and an extra a to get this d log a term. So the first one is a times h, or the conformal Hubble rate, times by this d log a, I'll redefine as f, and it depends on omega of matter, times psi of q and t. So the displacement field, we already described how to get that. These two are cosmologically determined, so it's your input parameter for your simulation. This thing you do have to calculate yourself, but if you look at the second order differential equation for calculating the growth factor, if you're doing a second order differential calculation, you're gonna have to get dd, dA anyway out of your solution. So this essentially comes from that. So solving for the growth factor will give you the F, but the F will just enter into the velocity initialization. So this is called the growth rate. And for CDM case, so CDM only, this thing is quite easy, is K independent. So you just have to calculate it once and then just put it in and the whole field will fall out as you expect. But if you move on to more complicated cosmologies where you have some scale independent growth, then this will also be scale independent, and that complicates this whole process. Scale dependent, sorry, yeah. So if you have a K dependence in your growth, then these equations technically still hold. You just have to do a little extra footwork. But yeah, now using this definition here, we can write the velocity field in K space at the initial time as I K squared, and the theta field of K E of I phi K. So this theta field is the velocity dispersion. Oh, sorry, yeah, divergence. So class and cam will again give you this, but in linear theory, this could be approximated to be the derivative of delta. So if you have the growth factor, then you can, if you have the growth factor and the power spectrum, you can technically approximate this. But if you want to do it properly, you can also just insert the velocity divergence field if you have it from class. Okay. Okay, so now we have the recipe for doing that. We have a way of getting the displacement field and the velocity field. Now we kind of get to a slightly subtle point regarding like how to get like two slightly different philosophical approaches to this whole procedure. And in literature, these are called the forward simulation. Or maybe it doesn't have a proper name, but I think of it as a forward simulation and the scale back simulation. So as we saw before, to get the displacement field and the velocity field, we just need the power spectrum at the time that we want to initialize the simulation. But the problem with doing this naively is that what we have derived in the n-body section is just Newtonian dynamics with CDM only. So you're essentially missing out on all of the other linear physics that could contribute at late times. So for example, metric perturbations, any residual radiation contribution if you start early enough. Neutrinos could also fall into here. And if you have some other kinds of I don't know, modified gravity or clustering dark energy. Whatever it is, all of these things, they are not included in the Newtonian dynamics that we are running the simulation forward with. So if I start the simulation with a power spectrum at the initial time given to me from class or cam, and I move it forward with CDM only, it's gonna be different to the power spectrum that I calculate from linear theory because they would be different by these contributions.
Or maybe a simpler way of saying is that the linear perturbation theory is fully general relativity compatible.
Yeah, exactly. So it's a full GR description, but the simulation is not. It's just a simplified Newtonian simulation. So these two different simulation methods, forward and scale back, are two different ways of tackling this problem of how to bridge the gap between linear linear GR theory and the Newtonian simulation that we have. So the older method, the more, I don't know if you call it canonical, but like the more old school method is the scale back method. So the scale back method is called that because rather than deriving the power spectrum at the time you want to initialize the simulation, we derive the power spectrum today. So we get the power spectrum as z equals 0. So that's our power spectrum calculated with full GR. So all of those metric perturbations and radiation contributions are included. And then we use a fictitious growth factor, the fic of t, to scale this back to the initial time of the simulation. I call this fictitious because this growth is not the real growth with all the linear theory components included. This includes only CDM clustering. So I'm assuming cold dark matter is the only thing that contributes to the universe's growth. So when I get back to here, this is going to be a fake universe. Because if I compare this to the real power spectrum I get at the initial time, these two are not going to be the same because I use the fictitious growth factor to scale them back. But the advantage of this is that now that if I scale it back and I use this, let's call this fic as well, just to keep notation clear. So if I use this fictitious power spectrum to initialize the simulation and embody evolve this forward with CDM only clustering, then I'm going to get a nonlinear power spectrum today that has all of the linear physics from the radiation and metric perturbation baked in already by definition. But now I get the extra bonus of the nonlinear effects of the CDM clustering. So it's almost like we're doing this back and forth procedure only to get the nonlinear contribution from CDM and assuming all of the linear physics like radiation and that don't get affected. So in this way, that we'll make sure that this power spectrum on the linear scales, so for K a lot smaller than the nonlinear K scale, the P nonlinear of K will equal the P linear of K as Z equals 0. So to ensure that the linear side of the physics is pinpointed down before we do the nonlinear side. Yeah, and the other method is the forward simulation. This method doesn't, this method treats it in a different way by having the contributions added in during simulation rather than bake them in at the beginning of the simulation. So I start with the real power spectrum at the initial time. But as I'm embody evolving this forward, in the Poisson equation, so in a CDM only simulation, I would just have 4 pi g rho bar and was it delta CDM. So this will be the only thing I have. But in order to make sure that it does the linear theory as well, I add in the additional terms by hand at every single point. So now it's the total energy density, and I have Fm delta m plus the neutrinos if you have them, plus the photons if you have them, plus any metric perturbations if you have them. So all these additional terms, they're added in as like a hand-holding process for the entire duration of the embodied simulation. So that makes sure that once we evolve this nonlinear power spectrum to Zeta today, all of these things are included in there rather than being left out.
But your equations of motion for moving the cold dark matter around the box, they are still Newtonian equations of motion. So you're not actually solving geodesic equations.
No. So the FG delta G is meant to be like a very hand wavy way of trying to patch that in. Yeah. So the metric perturbation kind of tries to account for that.
Because that's another thing with the Newtonian approach, that even if you include all these gravitational effects, you're still potentially incompatible with special relativity because there's no causality folded into the picture.
Yeah. So that problem comes up if you have the box too big, because if you have a box super horizon size, and suddenly things are affecting each other when they're not supposed to. But for most simulations, if you keep to a very sub-horizon size box, then this is generally good enough at this point. So yeah, so that's two different approaches.
It doesn't violate like what's it called, like conservation momentum and so on, if there is an effect on, like if there is an effect on the non-linear clustering of matter from the photons and the neutrinos and so on, but no back reaction.
Yeah, so this is like a spectator contribution. So these things are added in, but they don't get to react to nonlinear physics. And it kind of makes sense if you assume that photon clustering is probably not going to be that affected. But for massive neutrinos, for example, if the neutrinos have a large enough mass, then this back reaction becomes more and more important. Then you have to like find a better way to do things. So this is only like a rough first order approximation for weakly affected components.
Yeah, okay.
Yep. Yeah, so it's hard to say which one of these is superior in a sense. The one concern people might have with the scale back method is what happens if you want to look at an intermediate redshift. So if this, for this method, because of the fictitious growth factor that we have assumed, we are making sure that we get back the right answer at today, because that's when we pinpoint it down as the correct answer. But what if I want to look at a Z that is larger than the, sorry, not larger, wrong way. So I want to look at a redshift that's smaller than the initial redshift that I started at, but larger than 0. So say like if I start at redshift of 49 and I want to look at redshift of 2, can I trust the answer there? Because it's technically being scaled back by a fake growth factor and scaled forward with a fake fictitious evolution. So whether the physics here is real enough is a concern.
But I can easily fix that by just matching to the redshift that I care about.
Yeah, so you have to start a simulation.
Yeah, but if I said if you say I'm interested in what happens at set of 2, then I can just do this matching game at the set of 2 rather than set of 0.
Yeah, that's right.
So the statement is simply that if you match a set of 0, maybe you can't trust the intermediate results.
Yeah.
Okay.
So it might be a bit resource intensive, because if you do care about several redshifts, then you technically have to run the simulation several times to make sure that you actually believe it.
Which, and another point would be, can I, like if I actually want to have the snapshots in between because I want to do ray tracing,
yeah,
then you could potentially be dealing with something that is not actually correct in the intermediate redshifts.
So that's one of the main, I think one of the main counter arguments to this method. The forward simulation technically doesn't suffer from this, because you are ensuring that you do this forward evolution as correctly as possible. So at any intermediate redshift between the initial redshift and the final redshift, you do get back a more believable answer. But I think in reality, the differences at low redshift is very negligible. So at high redshift, when you think these two might deviate, you will have other problems to worry about, for example, transients. So after transients have died down, I think the difference between the two is ignorable. So yeah, okay. Any questions so far about these, the theory side of things? No, we're all happy? Okay, cool. So then let's move on. Let me clear a couple pages. Okay, so now what we want to look at is one particular program, and it's called Ngenic, or NGen-IC, I don't know how Volker Springer wanted it pronounced. It's written by the same author as Gadget 2, so it's meant to work closely with Gadget 2. The structure is fairly basic. It does one thing only and does it very well. So it's actually a good framework for additional modifications. So it's a good like base code for you to learn. And if you want to add in additional physics, it's a pretty good whiteboard to use. Okay, and the problem is that this code is very old and it's been done by many people over a long time. So it has a lot of features that due to legacy reasons, or maybe just someone once upon a time did it that way and now we all have to just follow his instructions. But it's not to say that you have to do it. If you want to go back in the code and patch these oddities out, you can. But at the end of the day, it's maybe 5 minutes more of work that you have to put in to just live with these inconveniences. So I never bothered to patch these out, and the current form is perfectly capable of doing what it's designed to do. But I know some people might ask, like, why am I multiplying by these random factors? Okay, so the purpose of the code is to write a binary file, a binary data file with all the particle information. So then gadget 2 can then read this binary file and know where all the particles are at the initial time. So the actual writing is not the bulk of the code. It's quite easy. It's just, if you look at it, it's just a one-line C code for fwrite. But the main part is how to actually derive the displacement field and the velocity field on the 3D grid, which is what we went through before. So that's the bulk of the actual work. So, okay, this is when you have, I might have to go into a bit detail with the actual numerical implementation for those that are interested. So like Marcus correctly pointed out before, that if we have a real displacement field in real space, once we Fourier transform into K-space, it will be complex. But we want to make sure that we construct a complex displacement field in a way that when we inverse transform back into real space, it stays real. So we use the fact that a real to complex FFT produces a K conjugation symmetry. So what essentially means that in the crude 1D example, if you have a set that's in the real space that has n data points, once you Fourier transform into K space, you have technically n, so this is n real numbers, but in K space you will have n complex numbers. So it feels like you got way more information because now you have 2n number of degrees of freedom. But the second half of the array are complex conjugations of the first half. So really you only have n on 2 number of complex numbers that are actually independent. And the other half are just, you can derive from the first half of the array. So when you generalize this to 3D, what that means is you only have to build half of the K grid. So once you build the half of the K grid, the other half can be derived with complex conjugation, so you don't technically need it. And FFTW doesn't really want to know about it either. So FFTW only wants the actual informative half of the array. So to construct this half K grid, remember we had in the displacement field, the Gaussian random noise needs a random amplitude and a random phase. So we need 2 random number generators to do this. And these 2 random number generators, they're not strictly random in the most natural sense. They're pseudo-random, which actually is good for us, and I won't explain that right now. I'll explain why having pseudo-random number is good for us later. So, but anyway, yeah, you generate 2 random numbers from some seed, and you use these numbers to go on the K grid. At every grid point, you want to generate a new random number and a new random phase to use for the displacement field at that point in K space. So if you want to go into NGenic and look at how this is handled by FFTW, then you need to work with the C array, which is extremely annoying because it's technically a 3D array, but C wants to represent them in 1D. So if you want to access on the 3D K grid, the point X, Y, Z, it is given by X times the number of Y grids you have, plus the Y point that you want, times the number of Z grids plus Z. That gives you the X, Y, Z point in that array. So this is the row major format. The reason it does that is because these points are adjacent to each other in memory. So when C iterates through this array, it saves a bit of like computation time because it doesn't have to look in the RAM for these points. You can just cycle through them easily. Yeah, there's also a column major one, but I don't think FFTW uses that. So, okay, and an extra oddity with this is that, so you have the real FFTW array, and let's call this size n. Then you expect the Fourier FFTW array to be size n divided by 2. And each one's a complex number, so you have 2. But if n is an odd number, so if n is odd, then you realize that you actually don't have enough to store all of the Fourier FFTW information. So you need to pad the real array. So the real array size must be n plus 1, I think. Yeah, so it must be n plus 1. So this 1 is what they call padding. So this is to make sure that you actually have enough memory once you go into the Fourier space to store n on 2 number of complex numbers. So yeah, and this half box, you don't you can divide it however you want, but in the FFTW convention, you cut the half along the last variable. So in a X, Y, Z way of labeling the axes, we cut the Z in half. So I technically cut the 3D box along the KX, KY, 0 plane. And okay, and this has a non-trivial shift of the origin from the real to Fourier space that you need to be mindful of. So the way you, in the real space grid that you set it up, how you determine what the X, Y, Z is that you assume one corner of the box is 0, 0, 0. And then as you increment along any direction or all 3 directions, you start going 0, 0, 1, for example, or 1, 0, 1, and 0, 1, 1, or whatever. Then you start making the vector your real space vector longer and longer, but you're keeping this as your origin. So your real space vectors go along like this. But once you go into Fourier space, your origin gets shifted to the center of the box. So rather than having your origin at the corner, your origin is now here. And since I've cut the box in half, then all the K vectors are from the center to some point in my half box. So these are my K vectors. So you might see some weird wrapping around operation in the code. It's because in the actual array itself, the K array still starts as 0. So it starts the 0th element of the Fourier space FFTW grid array is still the corner of the box. So then you have to then artificially shift the other sides of the box behind you in order to pretend that you're actually in the middle of the box. So what that means is if you are here, as long as I'm going within half the box side length, all of the K vectors are treated the same. So these are okay, these are fine. But as soon as I have a K vector that reaches over half the size of the box, this then gets actually pointed in the other direction. Other direction like this. So this is, you're not allowed to be there. So these kind of K vectors, because this point will be some position in the Fourier array. You can't do anything to change that because that's in the C memory. So to physically represent it as a half box, you just shift these arrays behind you into the other side with only this length. And same thing, if you accidentally reach on this side, you cut it off here and you redirect the other direction with just this length. So now you've physically pretended that you are actually in the center of the Fourier box. It's a very subtle, like, computational thing. So if you just want to run CDM simulations and you don't ever want to modify the code, you don't really need to know this. But if you want to do any modifications, then you have to keep this in mind when you're going to fiddle with the grid. Any questions? Because this is probably the weirdest part.
was just wondering, like the reason he does things the way he's doing is because he wants to save memory or save some trouble. So the point is, does generating initial conditions take so long that you have to worry about, you know, the extra second that the computer wastes?
No, it's just because FFTW works like this. So I think short of writing your own Fourier transform library, you just have to play by their rules.
Okay.
So for example, Simon Bird in Gadget 3, he just wrote the whole thing himself. He's like, whatever, I'm not using FFTW anymore. Yeah. Okay, so yeah, now that you have done this, then the rest of it is just exactly how I said before. You have your power spectrum at your initial time, however you derive that, either with a scale back or scale forward method. And then at every single K grid position, you generate your psi field and your V field. And there, you're done. So now, how do we input this into NGenic is where the first legacy feature comes in. So this power spectrum needs to be presented in two columns. So one column is, bear with me, it's log base 10 of K, and K is in MPC, H on MPC. And the second column is log base 10 of 4 pi K cubed P of K times K of 1 minus NS divided by 2 pi cubed. Like, let me explain what happened here. So this log base 10 and the K cubed are completely useless because as soon as NGenic reads the file, it takes the power of 10 and then divide by K cubed. So I have no idea why it does that. So you can very easily go into NGenic to saying, okay, don't take the power of 10 and don't divide by K cubed. So you can just put in the power spectrum in. This 2 pi cubed comes in because there is a box factor that you have to multiply in the displacement field algorithm that goes like the box length. It's 2 pi cubed divided by the box length. So this 2 pi cubed is cancelled out with this 2 pi cubed. So if you go into the box factor in the code and you get rid of this, you also don't need to do this multiplication either, or this division. The only really meaningful one, this 4 pi is here because the way that they define sigma 8 is slightly different in NGenic. So to not make it think that you got the sigma 8 wrong, you have to add this 4 pi in to convince it. And then also this K of 1 minus NS, you can probably remember this is the spectral tilt. So the reason you do this to factor out the spectral tilt is because NGenic insists on doing the spectral tilt for you. So if you put in a power spectrum that's already been tilted and then NGenic does it for you again, then your power spectrum is going to be wrong because it got tilted twice. So this is to untilt your power spectrum before letting NGenic do it themselves.
But you do have to specify the spectral index as an input parameter for NGenic?
Yeah, so you could set it to 1 in NGenic.
Set that to 1 and feed in the proper power spectrum.
Yeah, exactly. Yeah. So you could tell NGenic to not do it. Yeah. So like, I don't know, I find myself sometimes get confused with the parameter files if I have these like parameters set not the same as my specifications. So I prefer to just factor them out. So I have this consistent set of parameter files I could like go back and check on and not have to ask what happened. But yeah, this is also a bit of an oddity. If you go into the code and just tell NGenic to stop tilting your power spectrum, then you can also not do this. But that's just what NGenic wants. So in the zip file I sent, there is a mathematical notebook in the IC files folder. So that mathematical notebook basically does exactly this for you. So I might just share my screen we can have a look. So here, I'll share this screen. Okay, so yeah, this is the mathematical notebook, IC formatting. So here I imported the linear power spectrum I got out of class. So this is 00049, just to check. And yeah, you let class interpolate it and you plot this. So you can see that the blue line is the Z of 0 power spectrum and the orange line is Z of 49. So they're kind of different from each other by a pretty homogeneous shift. And I calculated the growth factor with a different code. So you just have to trust me that this is the growth factor to get you back to Z of 49. And you can check the blue line is the, okay, not the integrated response, it's the linear growth. And the orange line is the ratio between the two class power spectrums. So it's not quite the physical correct growth. So it's fictitious, but on average, it will get you the correct thing back. So then I rescaled the Z of 0 power spectrum back to Z of 49 by multiplying by the growth squared. Okay, I actually made the labeling mistake, so you have to change that. So you can see the rescaled power spectrum differs slightly with the real Z of 49 power spectrum from class on the large scales because I didn't account for any of the radiation and the GI effects. So there's some linear theory differences. On small scales, it's fairly okay. So if you didn't do this rescaling and you simply use the linear power spectrum to initialize, then your final answer is going to be out by this fraction. And yeah, here you okay, so you have to delete all these.
But that's only assuming you simulate your simulation box is that large that you can actually resolve those scales.
Yeah, which is highly unlikely.
Yes.
So yeah, so this IC output thing is basically taking a log 10 of the K and then taking the log 10 of 4 pi times K cubed times the power spectrum, rescaled back, times divided by 2 pi cubed, and then this is the spectral tilt. So my spectral tilt NS is 0.963. Oh no, I relabeled these wrong. So you guys have to delete all these new, so it's actually just M02, or maybe I'll resend this file around. And yeah, so now if you export string, now you get these two columns. So the log 10K and the log 10 blah, blah, blah times P of K. So this is you get this out and that's the text file you want to give Ngenic. So I called it this. So it has to be a .txt file. Okay, Mathematica gave me a CSV file, but like Ngenic wants it delimited by space. So you just have to control F or the commas into space. And so this is a file you're going to be putting onto Ngenic. Any questions on this one? Okay. Yeah, okay. Actually, yeah, how about let's take a 5-minute break now, and then we're going to actually try to generate an initial conditions. Resume recording. Okay, so yeah, now that we have the input power spectrum prepared in the file, in lambda CDM concordance cosmologies with reasonable parameters, like it's not necessary to explicitly input the velocity field. So you don't need the theta field because there's a good approximation for the growth rate F as a power of the omega m. So the code will take care of the computation from the displacement field solutions. But if you want to do anything with a non-trivial scale dependence on the growth in the growth factor, then the function needs to be modified to actually compute the velocity field separately because the approximation that Ngenic inherently uses for lambda CDM will break down. So in terms of cosmological parameters, most of the pretty, actually, how about let's look at the parameter file. So I'll share my screen again. Okay, so in the, oh, I just lost it. So where was it? Embody. Okay, so in the Ngenic file folder, you will have the ICS.params. So that's the parameter file. You can call it whatever you want as long as .param. So you get all these cosmological parameters that are pretty self-explanatory. So the omega just refers to the total matter omega. So this capital omega is the dimensionless density fraction. And omega lambda is how much cosmological constant you have. And the baryon density, this parameter, you can set it to non-zero if you want, but it doesn't actually do anything because this is only used for hydrodynamic simulations. in just pure particle simulations, baryons and CDMs are treated the same as just clustering non-relativistic cold matter. So this is kind of like a redundant parameter for lambda CDM simulations. And the Hubble parameter is just the little h, not the capital H. And this is the starting redshift that you want to be at. The sigma 8 is also another redundant parameter because NGENIC needs this if you feed it the power spectrum from today as Z0, and then NGENIC will do the scale back for you. But since we computed the Z49 initial power spectrum already, then we don't need NGENIC to do any rescaling. So the sigma A normalization is not a meaningful parameter.
So do you mean that you actually went into the code and switched off the part that does the scale back?
No, there's a parameter that can,
Right.
tell it to not scale back, yeah. So yeah, the renormalized input spectrum, this is the parameter to switch off. If it's 1, the NGENIC code will do the scale back for you. If you set it to 0, then NGENIC will just pretend like that power spectrum is already been properly normalized and all the units are correct and you don't have to touch it. Okay, and which spectrum, this is the choice you have. So this tells you what power spectrum to use for initializing the displacement field. You always want to set this to 2. So 2 means that you read off the tabulated file, the text file that you inputted. The option 1 uses Eisenstein-Hu, which is a fitting function from like 20 years ago that gets like a no wiggle power spectrum out relatively correctly. But nowadays, if you want to do anything serious, you don't want to use these approximations. I think 0 is is Starfu, which is a different kind of so even worse parameterization. So for any realistic work, you always want to set this to 2 and input your own power spectrum. And the name of the file that you stored the input power spectrum, the 2 columns that we made before, is in this. So you call it whatever you want. So before, I think we called it N002 ICZ49.txt. Okay, the one thing that you do have to be really careful of is the units. So all the units in Gadget's internal code has been set to centimeters and grams. So you need to set the length units to the correct unit of your input power spectrum. So in the case of megaparsecs per H, then you need to set, so internally right now, the stock standard NGENIC is set to this 3.0857 times 10 to 21. That's kiloparsecs on H. That's probably because Volker is someone that does galaxy simulations, so KPC makes more sense. But for us, we want MPC because that's what class gives us. So you have to change this to 24 to change from KPC to MPC. This solar mass definition is fine, you can leave it. And this velocity is in kilometers per second, and you can also leave it. If you want to import your own velocity field, then you've got to be careful to also set it to kilometers per second if you have velocity units in there. And and this number of files written in parallel just tells you how many files to write the output power snapshot, the binary file in. Normally, if you have a small enough simulation with like 512 cube, 100 million or less particles, you can get away with doing just one file in parallel and makes things easier. But if you go up to like 1 billion particles or more, then it complains that there's not enough buffer to write the file. So you have to do more in parallel. So you have to allocate more CPUs to the task, but you can do, say, 32 files to be written in parallel. So the output file will have 32 like almost identical cousins. And Gadget knows how to read these parallel files, so you don't have to do anything fancy with it. That's fine. The shape gamma parameter is not used because that's only needed for the Starfu power spectrum, which you generally don't want to use, so don't worry about this. This primordial index is the NS index I was talking about before. So if you factored out the NS in your input power spectrum, then you want to put this to be whatever index that you actually have in the real cosmology. But if you didn't factor it out and you don't want NGENIC to double do it for you, then you can just leave it as 1. Okay, and the important one here is the seed. So this is the seed that I mentioned before that you use to generate the pseudo-random numbers for your displacement field. This seed is pseudo-random, so that means if I use the same seed and I do the random number generation twice, I'll get the same sequence of random numbers. And that's a good thing for us, because if you want to compare two results from a simulation, sometimes it's good if you're changing the cosmological parameters, it's good to keep them the same seed, so then they will have the same random systematic noise. So then you can take the ratio and all the noise will exactly cancel out. And the difference you have left is just the physical difference caused by the parameter variation. But sometimes you also want to vary the seed. For example, if you're doing one particular cosmology and you have not enough particles, so you suffer from a lot of the sampling variance, then having different seeds to average over many different runs will suppress those kind of systematic noise for you. So yeah, we'll go into the noise bit a bit further in the power spectrum estimation part. But yeah, this seed just tells the random number generator what to use. And now actually to determine the size of the box, you just put it in here. So here is a very large number because it's in KPC. But since we changed the length units to MPC, then this could just be an MPC. So let's just say 512 MPC on each box side length. And okay, the end mesh and the end sample, the end mesh is the size of the Fourier grid that you use to do the Fourier transform. And the end sample sets the Nyquist frequency, which is kind of redundant because the Nyquist frequency is also determined by the Fourier grid. So these two are generally just set to be the same because there's no reason for you to set end sample any higher or any lower than the end mesh. And to determine actually how many particles you have, this is where another like weird legacy comes in. So this is a tile factor and you have a dummy glass file. So these two things determine the number of particles. Rather than going through the Fourier grid and just say, I have a particle at every single grid point, NGENIC uses a pre-made particle file where they have a box and all the particles are put on regular grid points already. So NGENIC reads this particle distribution into at the beginning of the initialization and then tries to move these particles with the displacement field. So rather than initializing its own particles every time, it just reads this glass file. The problem with this glass file is that it only has 16 cubed particles in it. So it's in the regular 16 times 16 times 16 grid of particles. If you want more particles, then you have to tessellate this glass box however many times to get the number of particles you need. So for example, if I want 1 billion particles, which means I need 1024. So for 1 billion particles, I need 1024 cubed particles in the box. So 16 I'll have to tessellate each in each dimension 64 times. So I have a 16 length glass file, and I have to tessellate this 64 times to get 1024 glass particles along one dimension. And when I cube that, I'll get the billion particles. And if I want 512 cube particles, then I'll need to tessellate it 32 times. So this tau factor tells you how many particles you're going to have because it is physically the number of times that you are like copy and pasting this glass file. It's called a glass file for other reasons because you can actually do a glass simulation, but in this case, this is just a dummy grid, unperturbed particle distribution. So this is a bit odd. Sometimes, and usually you want to just set the end mesh and end sample to the same as the number of particles. So if you have 512 cube particles, you just set 512 cube end mesh and end sample. So yeah, and then these are just the standard things. So the file base. Yep. Was that a question?
Is that the reason why that you always have these really, multiples of two numbers on the number of particles that people use?
Yeah.
Is that the reason?
Pretty much.
Yeah, that's what I thought. Okay. I thought I had
think
other.
it also has to do with the fast Fourier transform. The memory user is most efficient if you don't split it over several blocks of memory, and blocks of memory are in part.
Yeah. So if you had a smarter way of putting particles onto the grid, for example, put 2 on each grid point, then you can have more particles. But then if you just do 1 each, then it's always a power 2 somehow. So, okay, so I'm going to show you how to compile the program now. So I'm on Katana right now, and so I'll just go to my home directory and the playground. So here I have the workshop zip file, so I'll just unzip it. All right, so go into the workshop folder. So go into ngenic. So the one file you have to change is the make file, because that's what going to be looking for all the different libraries that you have that the program needs. So yeah, so the FFTW library here, you need to include the include section and the library section. So on Katana, if you're using the zip file I gave in the folder I gave you, then I already preset it for it to work on Katana. So here you can find the FFTW library, and you specify which C compiler it uses, and also you need to tell it where the GSL libraries are and where the mpitch library is. And
That's a make file, is it?
Yeah, that's the make file. Yeah.
Did you load any modules?
No, I haven't printed up, but yeah. So if you have the module, so if you want to load modules on Katana, okay, let me just module purge. Okay, so now I have no modules, so I have to load. So module add GSL 2.6, module add mpitch 3.3.1, module add FFTW 2.1.5, the mpitch version, module add Intel, whichever one's fine. Module add GCC as well in case it complains. So yeah, that's all the modules you need. So now if you on Katana, you can ask what module I have right now, say module list, that tells you what modules are loaded right now, and just make sure you have the right versions of the FFTW. And if you have the make file configured properly, then all you have to do now is just make. It will complain about some like legacy C code that it's not kosher nowadays, but the rest of it will work just fine. So now you have the executable ngenic, and that's the binary file that you use to run. And you have to go to the IC files to move or copy over a copy of the power spectrum that we initialized before. So copy that to ngenic. And now you have to change the parameters like I described before. So let's do a super baby one. Let's just do 32 grid size, 32 Nyquist in a 512 MPC box. So for 32 particles, then I just need to tile the glass file twice because each one is a 16 cube. Okay, for the cosmological parameters, I actually do have it. So it's in the input IC file, the specifications. This tells you the cosmology that we're in. So you can set that. So for example, here, I don't have omega m. Omega m needs to be added up. Where's my calculator? Oh, it's hiding behind markers. Okay, so okay, I got omega CB and omega nu separately, so that's a problem. CB plus omega nu. Okay, so that's my omega m. So I set that as the omega 0.2648. Okay, that's good enough. And then lambda, omega lambda would just be 352. Omega baryons, I don't have to care about it. H naught is, the Hubble parameter is 71 for this cosmology. Let's start at redshift of 49. Sigma A of 0.8.
Hang on a second.
Yep.
What if they don't add up to 1? Does it do curve space?
Yeah.
Simulations as well?
It assumes, so in the time stepper and the Hubble expansion rate, it will assume you have a curvature term. Yeah.
But what they use to calculate F is still kind of
Flat, yeah. So it generally doesn't work out.
That's the reason why it needs to read in omega m, basically.
Yeah. Yep.
Unless you supply your own detail.
Yeah, in which case then you can do whatever. Yeah, so the input file, I think it's called IC049. Renormalize this input spectrum, don't normalize it because we did it already. And we factored out the spectral index, so we have to put it in, so 0.963. just call it the C12345 and just have one file running in parallel and change the length units to 24. Okay, so, and the file base, so the file base is the name you want to call this file. So let's just call this N002, N32, L512, seed1. And it's going to put it in the output directory IC. And that's it. So everyone following so far? Okay, cool. So write this file and make sure I have the ICS folder made. So now I just, okay, on Katana, don't run any programs on the head node, otherwise you'll get yelled at. So if you want to run a job, then you have to q sub I L nodes, ask for how many nodes, one node, ppn, so number of processes. In this case, we just need one because we're only writing one file in parallel. Memory, ask for just 15 gigs is enough. And wall time, I think the smallest one you can ask for is 1 hour. So once you submit this, it's going to take a while, maybe take a couple of minutes for Katana to find the free spot for you on the cluster, but then you'll be able to run things in like an interactive job. I already did that, so I'm already on a node that I could just start running jobs. So I just do ngenic. All right, so if you have more than one processor, then you do npi run np how many processors, ngenic, and then the parameter file's name, and you go for it. And see, so it finds 32 particles along each direction, and it reads the glass file properly. And this is the total number of particles you have, so you can double check this. So this, so 32 cubed should give me this number of particles, and that looks correct. So I set my glass file tile factor correctly. And some information like the maximum displacement and the interparticle spacing, not that useful. You could just work that out by hand. And initial scale factor, make sure that's actually correct according to the initial redshift that you wanted. So now if you go into your ICS folder, you'll have a input spec that just tells you the power spectrum that it read in for generating it. It's not that useful. The second one is the binary file that you would pass on to Gadget as the initial conditions file. And that's it. So if you want to make larger simulations, you just increase the tile factor, increase the number of mesh and n sample, or make the box however large you want. And yeah, if you have a different cosmology, set your cosmology parameter different. Make sure it just matches to the input spectrum that you supply. Any technical related questions? All good?
Just wondering where the H comes in.
The H comes in.
So you supply, all it does is that it gives you the initial displacement and it gives you the initial velocity field.
Yeah.
And initial displacement you generate from the power spectrum that you need anyway. And all it does is to sort of roll the dice to generate these random numbers and then multiply them in the correct way. Yeah. And then it needs to know about omega m because it uses some funny fitting function from whenever to estimate the F. The F. Yeah. Exactly. So where does H come in?
Oh, you need the conformal H for the.
No, small h because you have to specify H. You have to specify sigma 8 and all the rest of it. Is it just additional stuff that ngenic needs to know if it does the scale back?
A sigma 8 is for scale back only, but you need small h for the velocity because you have a Hubble in the prefactor.
All right, it's theta on h. Sorry.
Yeah.
You're right. Okay. Yeah.
Yeah. So yeah, it needs h.
Basically, it needs there's a conformal Hubble factor in there that it needs to know what it is, given what you have for small h, the scale factor, and the energy densities.
Yeah. Yeah. So
yeah, that's right. You're right. Yeah, it's actually h times f. I forget.
Yeah, so yeah, it's in the velocity prefactor here where you need the initial time Hubble and that stuff. Okay, so that's literally how you generate initial conditions. And there's not much else to it. You just now move this file to the gadget folder when you want to run gadget and ask it to read in this initial conditions. And you have to tell the gadget the same set of cosmological parameters, because the header file in this binary will keep note of all the omega m's, the initial time, and other things. So if gadget starts running with a different set of cosmological parameters, it will start getting suspicious and stop your run because there are more particles or more mass than I expected, and this doesn't look right. But yeah, that's pretty obvious.
How long does it take to generate one?
Order of like 10 minutes. For 1 billion particles, if you do 32 files writing in parallel, probably like 15 minutes tops. Yeah. I don't have enough memory to do anymore, so I don't know. Yeah. Okay. So in the folder I sent, there's a bit of there's a lecture note PDF. Then, and also I wrote down a checklist of all the things that you should do to generate initial conditions. So you first have to go to a Boltzmann solver to get the linear power spectrum. Pre-process the power spectrum into a format that NGenic wants it. So that's the Mathematica notebook I sent. If you want to do it in Python or somewhere else, it's the same. Just make sure that it's in the same format and delimited by a white space. And you need all these things for NGenic to compile on whether the cluster or your MacBook. And then you run the program using this line. So npi run np, the number of processes, and the parameter file that you specified for that run without a full stop at the end. Yeah. And yeah, for small simulations, for most simulations, a single processor is able to get this initial condition generated in a couple of minutes. Parallelizer for 1 billion particles or larger, because NGenic will complain. For some reason, Gadget doesn't complain. So you can ask Gadget to write output for 1 billion particles into only just one file, and is perfectly happy to do that. Okay, so now we can, move on to power spectrum estimation. This is, I think it's pretty like straightforward, especially since we already have our head around this whole FFTW grid and having the K grid, having only half a box in the K space. So the power spectrum estimation just goes through this half K grid and asks what is the density contrast delta on that particular K point, and then square it, and then average over the entire volume. So this averaging is the only additional work that we have to do. So what the averaging means is that in a box with K vectors pointing in every single direction, depending on which point on the grid you are at, depending on how you bin the K range, several K vectors pointing in different directions might end up having the same length. And since the power spectrum is not does not care about the vector direction K, but only care about the absolute value, length of K, then all these K vectors pointing in different direction with similar length could all be lumped together to contribute to the same bin of power. So you have to go through the entire K grid, note down the delta of K squared at every single grid point, and then also in another file, or like another array, note down how many times you have seen this K length. So usually you see this referred to as modes. And then at the end, when you're averaging, you divide by a number of modes inside that particular K bin. So the program that I found that's really good for doing this is GemPK, which is written by Simeon Bird. So GemPK here. So everything in this file, everything in this program works great and is pretty smart, except it gets the CRC convolution thing wrong, like I said before. So you have to go into the power spectrum file, and here you see at the so after every time it gets the power spectrum, it multiplies by this in window function. This in window function is the inverse CRC kernel, and he takes the power 2 for it, but really you should only have the do this once. So you have to go into the file and then change it. But for now, like, it doesn't matter. Like the result still look qualitatively the same. So when you're doing it, make sure to go into the power spectrum.c file to change all those lines. But for now, I'm not going to bother. So okay, for compiling this file, it's a bit different because GenPK needs FFTW3, so module add FFTW 3.3.8. So module list, make sure I have all the correct version of the FFTW. And GenPK also needs 2 additional libraries, the gadget reader and also big file. And both of them are written by Simeon Bird himself, so I have no idea what goes inside. But gadget reader pretty much just reads a gadget snapshot and turns it into like a workable format rather than just one giant array. And the big file does something similar, and I don't know what it exactly does. And you don't really need to know about it either. So go into gadget reader, and you have to change the make file as well. So the make file needs to know where actually, no, I think this make file is fine. So you can just compile the standard make file because all the path is going to look for the libraries themselves, so it's fine. So you can just make this straight away. And apparently it takes a while. No, not takes a while, like it takes 20 seconds.
So the binary file that you generated with NGen, is it in the format that you can already analyze for the power spectrum?
Yeah,
estimate?
it's exactly the same as a snapshot file from.
Snapshot.
Yeah, it is a snapshot. Yeah. So yeah, now that we made gadget reader, go back and unpack the big file master. So I already did that. If you using the zip file I gave you, the big file folder is already in the GenPK master. So here, big file, you can see inside everything's already there. So you don't have to worry about it. And in the make file for GenPK, so the power spectrum estimator, you have to first tell it where to find the gadget reader library. So in this case, we installed it in the folder just next door. So go back one and then go to gadget reader master. If you have installed elsewhere, just make sure this path is correct. And for the rest of it, you similarly need to, oh no, okay, Simeon Bird did a smart thing. You don't have to specify where things are because he already, oh, actually you do. Sorry. So here, the L flags, so the library flags, you have to tell her where the FFTW3 library is. So for Katana, it's in share apps FFTW lib. If you're on your laptop, it's probably like user local bin something. And once you have that, you can just make the GenPK file out of GenPK program. And yeah, usually it's quite easy. So now you have GenPK, this executable. So to use this program, you just do GenPK, and then you have 3 options: I, O, and no, just 2 actually. The third one I added myself, so you don't have it. So it's I and O. So I is where the input snapshot file is located. So the input snapshot file, let's just analyze the initial conditions we analyzed before, that we generated before. So playground, workshop, what's the place called? Ngenic, ICS, and that was called N002, N32, L512, S1. So that's the input file. .o tells me where to put this, put the output estimated power spectrum. So I like to put it in the same place as the initial, the snapshot, but it's up to you where to put it. I'm just gonna put it there. And after running it, so it reads through it, it sees as a box size of 512 MPC on H, so that makes sense. That's what we had. Has 32 cubed particles. This vector has 6 of them because Gadget has 6 different types of particles. Type 1 is gas. You never use gas unless you're doing hydrodynamics. Type 2 is cold dark matter. Type 3, 4, 5, and 6 are galaxies, halos, and other kind of stuff. But in reality, they are physically the exact same thing. So you don't have to like differentiate them. They just kind of been labeled differently. So if you're...
It's just that we have different types of particles, you can assign different masses.
Yeah, exactly, yeah. So for any lambda CDM only simulation, you'll only have the type 2 particle being non-zero amount. So 32 cube particle, that makes sense. And has this amount of mass. Omega M, make sure that's the same as omega M that we have. And this tells you the redshift of the snapshot. So redshift of 49. And that tells you total mass in solar masses or kilograms. Okay. No, it has to be grams. It can't be solar masses. There's too many solar masses. Is it? Is it in solar mass? Oh, is it 9 times 10^8? Okay, yeah, it is. Yeah, and the FFT grid that you use to estimate the power spectrum. So like I said, in power spectrum, you go to every K grid point and you count how many deltas there are. So this is the size of the grid that they use in the program. In stock standard GenPK, this will always just be double the number of particles you have, or like double the single dimension number of particles you have. So if it's 32 cube particles, it's going to use a 64 cubed grid. You can go in and modify it to have this be in a user settable way. If you want, let me know. I'll send you the modified version where you have the additional option to do that. But otherwise, setting it to be double the particle number is not the worst thing you can do. It usually works pretty well. So now if you go to Ngenic, I see this where I put the output file. So here you have the snapshot that we analyzed, and here's the power spectrum that we have out of this snapshot. So it's just called PK dark matter power spectrum, and the base file, the base snapshot that I read off is the one that we have. It's a text file. Yeah, so it's a text file with 3 columns. The first one is the vector K, the length K. Second column is the power, and the third column is the modes. So this tells you how many modes for that particular K value that it found on the grid. So as you expect, the very small K have small amount of modes, and the larger Ks have higher modes until you get to very large K. That's the size of the box, so you only have 1 mode. The one annoying thing about the GenPK is that these are not in physical units, these are in Fourier units. So if you want to plot this power spectrum, you have to bring them back to, you have to multiply by factors to put them into MPC on H. So Simeon Bird actually documented this quite well. So if you just go on his GenPK GitHub page, you can see here, he tells you that if you want your power spectrum and K to be in MPC on H, you have to multiply the K column by 2 pi divided by the box size, and times the power spectrum by box size cubed. So you need to do this to make your power spectrum plot actually in the correct units. Another thing you can change. So yeah, I think maybe you can. Okay, so yeah, we can fetch this off the cluster to demonstrate how that works. Sure. Okay, so to fetch things off Katana, okay, I won't go into detail on how to do this now, but okay. What? No file, no such file directory. Okay, sorry, forgot one. All right, there we go. Got it. So now I have this file. So go to Mathematica. I'll plot this in Mathematica. So PK equals import. Yeah, so here, that's the file. PK interp, so list interpolate the PK, the first column, the second column is the power, so I need to multiply by the box size cubed. And the first column is the K, so times by 2 pi, divided by the box size. And now if I log plot this, 1. Oh, what happened? This is awkward. No, I didn't. I think, did I get the right box back? Yeah, I did. Is it just because the resolution is so bad that it's just... Okay, it's very possible that with 32 Q particles in 512 box, the resolution is so bad, this is actually the only section of power spectrum we can actually believe. So how about making a slightly larger simulation? 64 cube particles. All right, let's hope this works. Okay, slightly better. Okay, that looks like a power spectrum. Okay, it dips off at the end because of the noise. So if I now also import the linear power to compare, so compare this to, this is the power spectrum that we initialized. So now if we just compare this to the linear power spectrum that we initialized with, compare this to linear PK. It's kind of close. So the orange line is the class power spectrum, and the blue line is the simulation, the initial conditions that we generated. Because this, I used the Z49 one, so I should have used the Z01 and scaled it back. Okay, it's not so much better. Okay, probably just need more particles. But yeah, so, sorry, is it? Did I do something wrong?
Not enough particles.
Yeah. Okay, so yeah, any questions about what we did so far? So the power spectrum part is a bit quick, but really the physics is pretty simple. You're just kind of counting the number of deltas you have at every K grid point, and yeah, averaging over the number of modes. Are people happy about this?
So one question. So I tried to compile, let's see, what is this? GenPK, and it can't find FFTW3.
Oh,
Do I have to load that module separately?
wait, are you, yeah, are you on Katana with this module loaded, FFW 3.3.8?
Oh no, okay, no, I loaded 2.1.5.
Yeah, you're gonna have to unload that before loading the version 3.
Okay.
Yeah.
Okay, so different tools use different FFTW models, and so you have to compile them separately.
Yeah, so yeah, you can compile them separately, and every time you use them, you have to load the correct module, but you don't have to recompile them.
Ah, okay, so to run Gadget, I load FFT2, FTW2, then unload that. Okay, okay, fair enough.
Yeah,
All right, thanks.
no worries. Yeah, okay, so to summarize, basically for the initial conditions generation, what we described today is all the scale back method. I didn't describe how to do the scale forward method because that's a completely different embodied code. So for scale back method, we need the power spectrum today, and to calculate the growth factor, the linear growth factor, you have to do that yourself, and then scale it back to the initial redshift, and then put it into the weird format that Ngenic wants it. And yeah, and that's pretty much it. Yeah, you can, if you want, you can also email me. I could send you the code for calculating the linear growth factor, but it's really just like a second order ODE. You can solve this in Mathematica or C, whichever one you want. So that one is not that interesting. It's pretty much just a straightforward run kata. Yeah, so that's all I had want to do for today. So tomorrow we'll run the actual gadget, and with the initial conditions we generate, we probably want to go back and generate a slightly larger initial condition to make it a bit more believable, but the gist is there. Yeah, any questions? No. Oh, good then. Well, thanks for coming. I'll see you guys at the same time tomorrow.
That's good. Thanks very much for doing this.
No worries.